Swayam Prabha. Digital India. Educated India.
Welcome to this lecture number 14 on the NPTEL course for fluid mechanics for undergraduate students in chemical engineering. So, let us briefly review what we did in the previous lecture. We started doing integral momentum balance, especially we tried to apply the linear momentum balance to a control volume. Okay. So, let me briefly outline the key steps before from which we arrived this integral momentum balance. The starting point, if you remember, of all this was the Reynolds transport theorem. The Reynolds transport theorem relates the time derivative of a quantity like mass, momentum or energy for a system to the time derivative of any of these quantities that corresponds to a control volume. Okay. A system corresponds to, as you will recall, a fixed or identifiable piece of mass, whereas a control volume is a stationary piece of volume that you have constructed artificially to describe or analyze a problem. Okay. So, let me first write down the Reynolds transport theorem. So, the rate of change of a quantity like mass, momentum or energy for a system where capital N can be any one of the three, mass, momentum or energy, okay, is equal to the rate of change of the same quantity, time rate of change of the same quantity over CV, where we will use this notation where eta is n, the quantity per unit mass. So, if eta is mass, if n is mass, then eta is 1. If n is momentum, then eta is just V. Okay. So, rho is the density of the fluid, mass per unit volume, okay, and integrated over the whole volume in the control volume CV. But this is not all, because we realize that there can also be fluxes at the surfaces which bring in or take out material and thereby also bring in or take out mass, momentum or energy. Okay. So, V dot B, this is the term that corresponds to the inlet, the entry of momentum or exit of momentum by virtue of the flow into or out of the control volume through the control surfaces. So, this was the Reynolds transport theorem. Now, the linear momentum balance is essentially a statement of the balance is essentially the Newton's second law of motion applied to the system. The Newton's second law says that the rate of change of momentum in the system is equal to the sum of all external forces acting on the system. Sum of all external forces acting on the system. Now, the Newton's second law cannot be directly applied to a control volume, because a Newton's second law is applicable only for an identifiable piece of matter, which is what the system is, whereas a control volume is not an identifiable piece of matter, because fluid can come in and go out, and therefore, it clearly cannot be called as a system. Okay. So, Newton's second law cannot be applied to the control volume, and it is in fact applicable only to the system. But as I have told you in the last few lectures, it is always easier for us to carry out our integral balances in the control volume framework, because in most practical applications we are concerned only with whatever is happening within an identifiable piece of volume. We are not interested in following the same set of mass points in a fluid, because the fluid will come and go, but all we are interested in is whatever is happening in a control volume. For example, in applications may involve a pump or a compressor or a turbine, in which case we are interested in calculating the power requirement for a pump. So, our CV will essentially involve the pump, and we are not clearly interested in following the same set of fluid masses, okay, as they flow through the pump. Okay. So, the Reynolds transport theorem is very critical in transforming this time derivative to the control volume framework. You have to convert this to control volume framework using Reynolds transport theorem. Okay. And in order to do that, first we have to say what is P system. The momentum present in the system is the volume of the system, integral of the volume of the system times rho times velocity dV. So, in our lectures V with a cross is denoted for volume, whereas V is the symbol denoted for velocity, and since velocity is a vector, I am denoting it with an underscore. Okay. Now, so and first of all, the Newton's second law says dP dt for the system is sum of all forces, okay, and we know what is P for a system. P is essentially rho V dV for the system. V system is equal to sum of all forces acting on the system. We discussed in the last lecture that the forces can be divided into surface forces, which act only on the surface of the system, and the body force which act through the entire volume of the system. So, the body force typical example is the gravitational force, surface force example is pressure force and other viscous stresses that act only on the surface of the control surface of the system. Okay. So, we now use the Reynolds transport theorem to write dP dt of the system to be d dt over the control volume rho V dV. Okay. This is the rate of change of momentum present in the control volume. The control volume is not changing with time, okay, plus the flux of momentum in and out of the control volume through the control surfaces rho V dot N dA. This is the time rate of change of momentum of the system written in terms of the control volume variables, which is what is most convenient when we try to do problems using integral momentum balance. Now, this is equal to therefore, the sum of forces, namely the surface force and the body force. So, this is all there is to it when you want to use the momentum balance. Okay. Now, we have to understand what are the various forces that are acting on the that can potentially act on the control volume in various applications. The usual forces, as I have been telling you, the body forces typically that we will encounter is due to gravity. So, we have to simply use rho times the acceleration due to gravity vector g integrated over the control volume, and the surface forces are due to pressure. Suppose you have a control volume, okay, or there can be forces that are exerted on the surface, and these forces can have a normal component as well as a tangential component. The normal component is usually due to the pressure, whereas the tangential component can be due to viscous shear stresses. These both constitute the surface force. It depends on, they act on the surface, but the direction in which they act is different. For normal forces, they act in the direction along the unit normal, whereas in the tangential forces, they act in the direction perpendicular to the unit normal. That is the only difference. Usually, the viscous shear stresses that act on a control surface, although they are important in many applications, they are extremely difficult to know a priori. And in order to have a very good knowledge of viscous shear stresses, we will see that little later in the course that we have to use differential balances in detail to compute or to have an idea of what are the viscous shear stresses acting for example on a wall of a pipe and so on. So, usually because it is difficult to know a priori unless you have detailed experimental data or you solve the differential balances, which we will see later, this is often neglected at this point, okay, the viscous shear stresses. So, if you have a control volume, usually the only force that is taken into account is the pressure force. Okay. The only surface force that is taken into account, I am sorry, is the pressure force, and the pressure, as you have seen in the first few lectures on hydrostatics, acts in the direction of minus n. Pressure is a scalar number, it is a number, okay. It is not a vector. So, pressure is just a scalar, but it acts always in the direction opposite to the unit normal, outward normal of a surface. Pressure is compressive in nature. So, it tends to compress the volume element. So, it acts in the direction opposite to the unit normal. So, if you want to write an expression for the pressure surface force due to pressure, okay, all you have to do is to say that integral over the control surface P time minus n dA, because pressure is just a number, it is a scalar number, and it is the magnitude of the force that is acting compressive that tends to compress a given volume element. So, we have to put in the direction, and since it is compressive, it acts in the direction of minus n. So, we have to explicitly put minus n while calculating the surface force, and you have to, since the pressure can in principle vary at various points along the control surface, we have to integrate the pressure over the entire control surface to get the surface force due to the pressure forces. The other thing that we reminded ourselves in the last lecture is the following, that suppose you have a very simple problem. You have a fluid coming in like this. So, let the blue line be the control volume. This is, for example, a container in which fluid is coming in and going out. This is a very illustrative simple example. The blue line is the CS, whatever is inside is CV, and let us say fluid is coming in like this and going out like this. Okay. Now, the pressure, so the unit outward normal here is like this, the unit outward normal here is like this. Okay. So, here you may all agree that the pressure is in the direction opposite to the unit normal. So, you will argue that the pressure acts in this direction. Okay. So, P minus n is in this direction at the inlet. But what is important for you to remember or understand is that pressure at the exit or at the control surface of the exit is also in the direction P minus n, in the direction opposite to n. Okay. Just because the fluid is coming out, it does not mean that the force on this control surface is in the plus n direction. The key thing to understand here is that the force on this surface is exerted by the fluid outside, which tends to compress the fluid present inside, and clearly that is obviously in the minus n direction. So, this is a common mistake that one can make based on an incomplete intuition of the problem, that the pressure at the exit of a control surface is in the direction of the unit normal. It is not. Just as in the inlet the pressure acts in the direction opposite to the unit normal, tends to compress this control surface. Likewise, the pressure at the exit also tends to compress the control surface, also acts in the direction of minus n. Okay. This is a common error that one can potentially make. So, it is good to be aware of it. So, another thing to understand is, so let me just write down for your convenience the momentum balance again. So, after using the Reynolds transport theorem, Cv rho v dv plus integral over Cs rho v v dot n dA is Fs plus Fb. So, we have understood what is Fb, and we have said that Fs is usually due to pressure. Viscous stresses, although they are important in many cases, at the level of integral balances, at times it is not easy to obtain detailed information about the viscous shear stresses in a flow problem, and therefore, one often neglects it because of lack of information. Okay. Of course, one has to go back to the results and see whether the results make physically consistent sense after neglecting the viscous stresses. So, we will have opportunities to discuss this later when we do various examples here, as well as when we discuss differential momentum balances to understand fluid flow. But right now we know at a simplistic level what are the body forces, what are the surface forces, how to compute them. Now, another important thing to understand is how to calculate this flux integral. Rho v is the momentum density Okay. This is momentum per unit volume times V dot n dA is the differential volumetric flow rate on, suppose you have a control volume and you have a tiny patch dA and this is the unit outward normal. What is the volume flux, volume flowing per unit time out of this differential control volume? This is the V dot n dA. So, let me write it in red color. This is volume per time. So, this gives you the rate at which momentum comes inside to the CV or goes outside of the CV by virtue of inflow and outflow through the control surfaces to the CV. Okay. Now, what is important to understand here is how to calculate again this V dot n integral. Remember that in this simple example that we just pointed out, let me just, instead of drawing this again, let me go back there. So, let me point out that the velocity inside is coming like this. The velocity vector, obviously since it is coming in, it is in the direction opposite to n, while going out it is in the direction of n. So, V dot n is negative for inlets, while V dot n is positive by definition at an outlet. So, this is very important to understand that whenever you compute the surface flux term, the V dot n term will always be positive at outlets and negative at inlets regardless of the coordinate system you choose. Okay. Because in many problems you may choose a coordinate system as per the convenience of, as it is convenient to analyze a problem. So, for example, let me point out again this simple example. Suppose you have a container in which fluid is coming and flowing out, going out, and let us choose some control surface like this which demarcates the control volume from the surroundings. Okay. So, fluid is coming in and going out. You may choose a coordinate system like this. You may say this is x, this is y. Okay. So, let me write down the flux term like this, rho v dot n. This is the term that we are trying to understand carefully over the control surfaces. Now, there is no flow in this part of the control surface, this part of the control surface. So, the flow is only through the entry and exit. Now, if you have the coordinate system like this, okay, now I want to write the x component of the term. This is a vector equation, remember. So, we have to actually, whenever you solve a physical problem, you have to actually solve it component wise. Okay. Now, if you want to write the x component, now remember the vector velocity is written as u times I plus v times j plus w times k, where I, j, k are the unit vectors in the x, y and z direction, u, v, w are the scalar components of the velocity vector in those three directions. Now, if we want to write the x component of this equation, you first understand that this term v dot n is a scalar. So, you cannot make a component out of a scalar. So, the only vector available to you is v. So, the x component is obtained by just saying it is rho integral rho u v dot n dA. Okay. Now, v dot n at the inlet, so this is over all the control surfaces and this is over the inlet rho u v dot n plus over outlet dA. Okay. Now, here u is the x component of the vector v dot n. Okay. Even though the fluid is coming like this, okay, and you have rightly picked the x component to be like this, v dot n is still negative at the inlet, okay, because the fluid is coming in like this. Okay. So, n is pointing in this direction, v is pointing in this direction. So, v dot n is always negative. Okay. So, while at the outlet it is always positive. Now, in somebody else may choose to work with the problem in a different set of coordinate axes, where x is pointing like this and y is pointing like that. It is just the opposite, x is pointing in the opposite direction. Even so, whether v dot n is positive or not, even so, for example, if you want to analyze a problem like that with the new coordinate system. For example, just where, so I am drawing the control surface again, same control surface, all you are changing is all you are changing is the we are using the coordinate system like this. Somebody else may choose to work with this coordinate system for whatever reason. So, now what is important is velocity is coming in the minus x direction, it is going out in the minus x direction according to this problem. Okay. But the unit, all you have to understand is that the unit outward normal and the velocity vectors are pointing in the opposite direction in the inlet, and they are pointing in the same direction in the outlet. So, V dot n is negative at the inlet and positive at the outlet, regardless of what coordinate system you choose. Okay. That is because V dot n is a dot product. A dot product is a scalar, and therefore, it is independent of the choice of the coordinate system that you choose to work with. Okay. While the component u, if you compute for this problem, the numbers will come out to be negative of what you had for the earlier problem, because here your x is pointing in this direction and flow is like this. So, obviously, u is in the negative direction, x direction according to this coordinate system, whereas in the earlier coordinate system it is in the positive x direction. Now, that is of course completely equivalent, because you are just using a different set of coordinate system, but the calculation of V dot n is invariant or independent of the coordinate system. That is something that we have to understand very carefully. Now, another thing we pointed out in the last lecture is that, so since it is a vector equation, you may have to write the full scalar component. I am just giving you an example of the x component, f x surface plus f x body is equal to d dt over the C V u rho d v plus integral over C s rho u v dot n d a. Okay. This is all that you have to do for the x component. Similarly, you can write down equations for the y and z components, which we had done in the last lecture, but I will not repeat that. It's fairly similar. Okay. Now, another thing we pointed out is that suppose you have a closed surface, okay, and there is uniform pressure acting on the closed surface. Everywhere on the surface there is a uniform pressure. For example, you may have a system or a control volume which is uniformly exposed to atmospheric pressure. Now, in such a case, the contribution to surface due to pressure, if it is uniform, let us say there is a uniform atmospheric pressure, F s pressure will then be integral minus P atmosphere n dA. Now, P is constant, so I can pull it out, n dA. Now, if you have a closed surface, okay, and if you just evaluate n dA for a closed surface, just by symmetry this has to be 0. Okay. So, the surface force due to a uniform pressure force acting on each and every point on the control surface is 0. Okay. In many problems, you may not just have the atmospheric pressure, you may have something else in addition to atmospheric pressure. So, what will matter in such problems, if you have let us say a pump that is uniformly exposed to the atmosphere, the only thing that will matter is the difference between the actual pressure and atmospheric pressure, because the net effect of a uniform atmospheric pressure on the entire control surface is exactly 0, because all the components will identically cancel out. Okay. So, when you want to calculate the pressure force, all that will usually matter is the difference between the actual pressure and the atmospheric pressure, and you have to do it with it's in the minus n direction, okay, dA. This is nothing but the gauge pressure. This is something that we have defined. The difference between the atmospheric pressure, the actual pressure and the atmospheric pressure, if it is greater than 0, is called the gauge pressure, while if the actual pressure is less than atmospheric pressure, then we define a vacuum pressure, which is essentially P atmosphere minus the pressure. So, you just want to keep the number to be positive. If you calculate the gauge pressure, if P is less than P atmosphere, you will get a negative number. In order to keep it positive, we define the vacuum pressure as P atmosphere minus P if P is less than P atmosphere. Okay. So, this is something that we did in the last case as well. Okay. Now, let us try to illustrate all of this using a simple example, and the example is the following. Example of integral momentum balance. Imagine you have a solid surface of which I am drawing just a cross section, a solid surface like this, and far away there is a nozzle, okay, from which fluid is ejecting. There is a jet of water that is coming out, and it impinges on the surface which is at a distance. So, this jet of water comes and flows like this. Okay. Now, the question that and we are given what is the velocity. The velocity is in some we always want to put a coordinate system. So, let us call direction of the flow of jet as x and the direction perpendicular as y, and we are given some number for velocity v. It is some u times I, and we are given what is the area of the nozzle, the cross sectional area of the nozzle through which water is exiting. Now, the question that we want to know is that suppose you want to keep this solid surface stationary. This is a solid. Now, if the fluid continues to impinge on it, and if there is nothing to keep the solid surface in place in stationary, then the solid surface of course will accelerate, because there is a net force due to the momentum transfer conveyed by the fluid to the solid surface because of impingement. But we want the solid to be stationary. So, imagine that you are exerting a reaction force by holding the solid surface using your hand. Okay. So, you are holding the solid surface using your hand, and the jet impinges on the solid surface. Okay. So, the question is, what is the horizontal force on your hand? This is the question that we want to answer using the application of integral momentum balance. Okay. So, first is, as I have told you, is choose. In the last lecture we pointed out some tips or useful guidelines that will help us in solving problems that involve integral momentum balances. Now, the first is the choice of a coordinate system, and here it is pretty obvious what we have to do. We can choose a coordinate system, Cartesian coordinate system with one vector pointing along the direction of the flow, one unit vector pointing along the direction of the flow, which I will call x, and another unit vector in the direction perpendicular to the flow, which I will call y. Okay. And things are invariant in the third direction, that is the z direction. So, we will not worry about the third direction. Now, the first CV I will use is the following. So, let us draw the jet a little further up. Okay. The first CV I will use is this dotted line. So, just to make the idea clear to you, let us assume that the jet flows like this, okay, impinges and flows like that. Now, let us choose the CV such that it cuts across the water jet at the somewhat far away from the impingement, okay, and it is also cuts across your hand, which is holding the solid surface in place. Okay. Now, we are making some standard assumptions, steady flow and incompressible flow. These are all assumptions that the flow is steady, that is nothing is dependent on time at a given point in space, as well as the flow is incompressible, which means that density is a constant. Okay. And we will also assume that the flow is uniform. Okay. What is a uniform flow? Whenever you have a flow, let us say inside a pipe, okay, here you have a jet of water, which is surrounded by air, this is water. Okay. So, question is the velocity at each and every point across the cross section of such a flow same or not. Okay. If it is same, then the velocity vectors will be like this. Such a flow is called an uniform flow. And for water jets that exit from a nozzle to a free surface, it is a very good approximation to treat the flow to be uniform, because in reality also the velocity vectors are constant, they are independent of the cross section. Okay. So, this is an example of uniform flow. A velocity vector is independent of the cross section. Okay. Whereas, whenever you have flow in a channel or a pipe which are bounded by solid surfaces, we will see in detail a little later when we discuss differential balances, that whenever you have such a flow, the fluid velocity has to go to 0 at the walls, and there is a pressure difference that is driving the flow. So, the velocity is non-uniform, that is at okay. The reason why whether you have a uniform flow or non-uniform flow is important is because when you want to evaluate the flux term rho v dot n dA, this is an area over the inlet and outlet of the control surfaces. Now, if V is a function of the cross sectional area, then you have to evaluate the area integral. Okay. For non-uniform flows, have to evaluate the surface integral at inlet and exit at outlets. But if uniform flow is assumed, then u or the velocity vector v is independent of the cross section. So, can pull the velocity vector out of the integral sign. So, you will have rho v dot n dA. So, integral over dA is simply area of the cross section or the control surface. So, things become much simpler when flow is uniform. If the flow is not uniform, we need to have a knowledge of how velocity varies with the cross section. In order for us to be able to compute this area or surface integral, we will come to that a little while later. There are, for simple cases in flow through channels and pipes, once you know the cross section of the channel, there are some standard results which come from differential balances, which enable us to calculate these integrals, okay, in a straightforward way. But nonetheless, it is slightly more tedious than when you have an uniform flow, because in a uniform flow the velocity vectors are parallel to each other and they are constant, they are independent of the cross section. Therefore, you do not have to worry about evaluating any integral. So, in this example we will assume the flow to be uniform. When the flow is uniform, when you use the integral momentum balance, F s plus F b is summation over all the cross sections v rho v dot n times A. Okay. This is the momentum balance. The mass balance will simply reduce to summation over C s rho v dot n A is 0. Okay. Now, the thing that is important for us to understand is that Suppose let us go back to the problem. You have the surface which you are trying to hold by your hand, okay, and the CV is cutting across your hand. Now, since the CV cuts across your hand will have to exert a reaction force. Hand will exert a reaction force on the control surface. In order to keep the solid surface from moving, your hand is of course trying to resist it by exerting a force. And how is that force felt by the CV? It is felt via the control surface, because the control surface is cutting across your hand, okay, on the control surface. And let us call that reaction force R with components R x and R y. Okay. Now, the question that is being asked, the question that was asked to us to compute is the force that is exerted by the CV on your hand, which is exactly the equal and opposite of the reaction force exerted by the hand on the CV by Newton's third law of motion. So, what we have to compute eventually is R x and R y, okay, and the negative of that will be the force exerted by the CV on your hand, because they are just equal and opposite. Okay. Now, let us go further into the problem. Now, you have a free jet that is coming and exiting into and out of the CV. Now, whenever you have a free jet, the pressure of the jet is atmospheric and the pressure outside is also atmospheric. Okay. So, there is uniform atmospheric pressure everywhere acting on your CV. Okay. So, if you have uniform atmospheric pressure, then of course, it will not contribute anything. Now, let us call the force, the component x component of the force exerted by the hand on the CV as R x, because whether R x is in the direction along a plus x, or let us put a coordinate system x and y like this, and flow is in the plus x direction. So, whether R x is positive or negative will come out of the answer. So, we have to understand that the reaction force that is exerted by the hand on the surface is R x, but when we want to compute R x, and the negative of that is the force exerted by the CV on the hand. But right now, let us just keep R x to be acting in the R x is the component along the x direction. Whether it is acting in the direction of x or minus x will come out of the problem. That is, all I am saying is that R x is an algebraic quantity, it has a sign and it will come out naturally from our calculation, and it will agree with the physically expected result also, as we will see shortly. So, now let us just do the x component of the momentum balance. So, the sum of surface and body forces along the x direction is equal to summation over Cs u rho v dot n dA. Now, the body force is not, there is no body force in the x direction, that is 0. Okay. Now, what is f x s x? What are the surface forces acting on the control surface in the x direction? Okay. We have already said that the pressure force, uniform pressure force that acts on the entire control surface, that will act to 0 because it is uniform everywhere. So, one way to see it is very simple, that suppose you have the control surface to be like this, there is P atmosphere here and there is P atmosphere here on both sides, and of course, you have the surface and your hand is holding the surface, but there is uniform P atmosphere on both sides which will balance out, and that will not contribute to the surface force. The only thing that will contribute is the reaction force exerted by your hand on the CV through the control surface, because the reaction force is that there is a reaction force that is exerted by your hand on the CV is felt only through the control surface, because it is a surface force, and since the control surface cuts across your hand, that force will be transmitted as R x in the momentum balance. Okay. So, R x is equal to summation over the control surface u rho v dot n dA times A, because you have already integrated it out, it is a uniform flow approximation. Okay. Now, along the x direction there is only inlet of momentum, there is no exit of momentum. So, along the inlet you have R x is u remains u, v dot n, v is in the direction of plus x, whereas unit outward normal is in the direction of minus x, v dot n is minus u, u times rho times minus u times A at the inlet. Okay. So, this is equal to minus rho u squared A at the inlet. Okay. So, R x, since we know the density of the fluid, okay, is known, velocity is given, the average velocity that the jet is impinging is given, and the area of the jet is the area of the nozzle. This is an assumption that the jet is not thinning down as it impinges, which is an assumption. So, that is a reasonably good assumption to make. So, R x is minus rho u squared A, u squared is positive quantity, okay, u is the x component of velocity, u squared is positive, rho is positive, A is positive. So, R x is negative, that is your hand must exert a force in the negative x direction. Which completely agrees with our intuition, because the fluid is jet is impinging on the surface in the plus x direction. In order for you to keep the solid surface stationary, you should of course resist it with a force in the minus x direction. So, that is clear. So, the force exerted by the CV on your hand is negative of R x, which will be rho u squared, that is the answer. Okay. So, this is a very simple example of the application of integral momentum balance. We learnt a couple of things here, that whenever you have a free jet, it is it's a very good assumption to make to consider the jet to have uniform velocity, and the pressure inside the jet is also atmospheric. Whenever the jet is free, that is, it is exposed to the atmosphere outside, the pressure inside the jet also becomes atmospheric. That is a good assumption. So, once you make these assumptions, it is very easy to use the integral momentum balance to calculate the force. Now, I want to illustrate this with a slightly different choice of CV, because the choice of CV is completely in the hands of the person who is solving the problem. Therefore, we can always choose some other CV. So, I am going to illustrate this like this. This is the solid surface, okay, and your hand is holding it. Now, let me draw the jet with blue color. It's going like that. Now, the CV which I am going to draw with red color is exactly, it does not include the solid surface, it just adjoins the solid surface, and it encloses the fluid that is trying to impinge on the solid surface, but it does not include the solid surface. Okay. Now, let us call this area as AP, okay, and this is our new CV. We are going to apply the momentum balance now. Okay. Fsx, everything remains same as before, uniform flow assumption, pressure being atmospheric, everything remains same. A. Now, what is Fx x here? Now, there is clearly atmospheric pressure acting, okay, and there is a force exerted by the solid surface on the fluid. Let us call that force Bx. Okay. This is the force exerted by the solid surface on the fluid. Okay. Again let us not worry about the sign, it will come out naturally from the problem. Bx is an algebraic quantity, it is merely a component of the force exerted by the solid surface on the fluid, okay, on the control surface of the fluid. So, Fxx is therefore P atmosphere times AP plus Bx is equal to, now this is same as before, minus rho u squared A at inlet. Okay. That is because u dot n is v dot n is again negative for the inlet, therefore, you get this answer. So, P atmosphere, so we have this expression. Now, the question that we want is what is the force exerted by the what is the force felt by your hand. Okay. So, let us first eliminate Bx from here, it is rho u squared A inlet minus P atmosphere times AP. Now, we do a free body diagram on the plate. Okay. The force exerted by your hand on the plate is Rx, the force exerted by the plate on the fluid is Bx, but there is also an uniform atmospheric pressure acting on the plate from the right side. Okay. So, we will have to include that in the free body diagram on the plate. Okay. So, these are the only 3 forces acting on the plate. Since the plate is not accelerating, sum of all forces on the plate must be 0. Okay. So, that simply means 0 is equal to minus Bx. So, we have taken Bx to act in this direction, sum of all forces on the plate in the x direction is 0. Okay. So, let me explain this carefully. Bx is the force exerted by the plate on the CV. So, minus Bx is the force exerted by the CV on the plate by Newton's third law of motion. So, minus Bx minus P atmosphere AP, because that is acting in the minus x direction, plus Rx, we do not know what is the sign of Rx, whether it is positive or negative, it will come out naturally from the problem. Okay. So, Rx is nothing but P atmosphere AP plus Bx, but we already have an expression for Bx. So, it is P atmosphere times AP minus P atmosphere AP, okay, minus rho u squared A at the inlet. Okay. Now, the 2 P atmosphere AP will cancel to give Rx is minus rho u squared A at the inlet, and remember that Rx is the force exerted by the hand on the CV. So, the force exerted, this is the force exerted by your hand on CV. So, force exerted by CV on your hand is simply rho u squared A at inlet. It is clearly in the plus x direction as you would expect physically. Okay. So, this clearly tells you that you can choose to work with a CV of your choice, and the answer, if you do every step correctly, the answer will be invariant to the CV that you choose to work with. Okay. But some CVs are easier to apply for a given problem than other CVs. For example, in our example here, we had to do some extra work in the second CV, because we had to again draw a separate free body diagram on the plate in order to take the contribution of the atmospheric pressure out, whereas in the first CV we immediately concluded that the atmospheric pressure balances out. So, we had to merely focus on the force exerted by the hand on the CV, the Rx force, that is the reaction force. Okay. So, some CVs are more convenient than the other, but if you do all the steps correctly and carefully, all the CVs should give rise to the same answer, and clearly the physical answer, the CV is actually our construction. The problem does not care for CV. So, if you do the if the actual physical processes do not care for CVs, whereas if you want to analyze it, you choose a CV of your convenience, but the answer should come out to be the same regardless of the way in which the CV is chosen, so long as all the steps are done correctly. Okay. So, that is the key thing that we have to remember when we do momentum balance. I think we will stop here. This completes an example, and we will continue from this point onwards in the next lecture, where we will finish our discussion on momentum balance and we will start energy balance. Okay. Thank you for your attention, and we will see you in the next lecture.